Anyway, I'm going to start. As always, we try to review what's happening in the sky this month, and here's a little animation of the Lyrid meteor shower, which takes place later in April. Um, and I'll just remind you that a really good place to find information is this website called timeanddate.com. They have a lot of information on the rising and setting time of the sun and the moon, but they also have the planets, and they have lots of nice little animations that are worth looking at. So the moon is actually going to be full tomorrow night, although whether or not um, we'll be able to see it here, of course, we don't know. And it turns out that in April, there's another full moon at the end of the month. And while the full moon on April 2nd, actually, is called the pink moon, the second full moon of any month, and we have one in April, is called a blue moon. And I don't want anybody to ask me why that is, because it's all traced to traditions and it makes no scientific sense, but that's beside the point. Mercury will be visible in the early morning sky towards the east. The moon and Venus will be really close together on April 18th and 19th. The first quarter moon will be really close to Jupiter on the 22nd, and there is this Lyrid meteor shower. And as I said, this little video that I found, which shows where you can find it in the night sky. What you'd see would be a bunch of maybe shooting stars emanating from the same spot on the sky towards the north. Anyway, of course, we always have to worry about weather. Another interesting thing is the Artemis 2 mission to the moon is supposed to perhaps launch tomorrow evening. It's the first time that we send people out by the moon in a very long time. It's an interesting orbit, which is shown here. There was a really nice interactive article in the New York Times yesterday, if anybody has the New York Times and is interested in that. And it takes off and goes a couple of times around the Earth to kind of build up its speed. It gets actually accelerated by the gravity of the Earth after it fires its rocket to get it up initially. And then it goes in this slingshot kind of orbit around the far side of the moon and comes back. That's called a free return orbit. And you notice that it doesn't actually go into orbit around the moon. It does, however, go further away from the Earth than anyone has ever gone before. And this is really a test demonstration mission to test both the capsule, which is called Orion, and the rocket propellant system that it's going to send there. And after taking off, whenever it does take off, 10 days later, then it will splash down in the Pacific. So I think we're all excited to see what happens, um, because we don't we haven't done this for a long time. So we'll keep our fingers crossed. The first time it can launch is tomorrow evening around 6 o'clock. Okay, another thing that I know some of you are aware of, I'm involved in building the Fred Young submillimeter telescope. And in fact, I'm leaving for Chile on Sunday. We'll inaugurate the telescope on next Thursday, April 9th. It will be live streamed, so if any of you have nothing better to do and think that it might be fun to tune in and watch this event, if you go to www.ccatobservatory.org, you can click on this link and it will take you to another link, which is a Cornell link. And sometime I'll talk more about the telescope later on. This is a picture that was taken yesterday, and the weather wasn't great. Well, hopefully, I'll have some better pictures next week. But again, this is a radio telescope, so it's kind of weird looking telescope. It's this box, and inside there, there's not one but two mirrors. This is a special design of the telescope. And so the radiation comes in from the sky and bounces off this mirror up to this mirror and then over to this box here, in which there will be a gigantic camera, which people can walk into. It's so big. Eventually, you won't be able to see into the telescope. All this will be closed up. But they wanted to leave it open while they were putting the mirrors in, and they just put the second mirror in yesterday. So that's what I've been up to, and I'm pretty excited about this. Okay, but let's go back to more mundane topics. This in deciding what to talk about this time, I thought I'd pick something that was sort of standard astrophysics. What happens when a star dies? And in order to do that, we have to talk a little bit about how stars exist and why they die, in fact. And of course, we talk first about our sun and then talk about how other stars are more interesting than our poor old dear but otherwise boring sun. So let's just remember that the sun is 100 times bigger than the Earth. The sun looks something like this if you were outside the Earth's atmosphere and could take a nice picture of the sun. It's a very dynamic body, in fact. It has regions which are hotter and regions which are cooler, and sometimes it has these storms or prominences, as we call them. It's not just a ball of gas where everything is perfectly constant at a constant temperature and nothing is going on. It's a ball of hot, dynamic, glowing gas where things are happening. It is a lot bigger than the Earth. It's 1,000 times more massive than Jupiter, and it's 300,000 times more massive than the Earth. So again, we have to kind of stretch our imaginations when we start talking about stars. Another thing to understand is that we don't see into the sun the same way that we don't see inside of the Earth. We see the surface of the Earth. We see the surface of the sun. We call that the photosphere. But by studying the surface of the sun, we are able to learn about what is going on inside the sun, in part because we understand how physics works and how when you have a large mass of gas and you can configure it to be the size of the sun and even the interior structure of the sun, we understand what goes on. It's not magical. Later on, when we start talking about some of the results, the end products of stellar evolution, we'll find out that we don't understand the structure of what's inside either a neutron star or a black hole. So here's my little cartoon cutout of the structure of the sun. The outer part of the sun, which is only seen at eclipses, called the corona, and it is really, really hot, 1.8 million degrees on the Kelvin scale, and it extends for many millions of kilometers. Then we have the part that we can actually see, which is called the photosphere, and that has a temperature of somewhere around 6,000 degrees instead of 1.8 million degrees. 6,000 degrees is still very hot by human standards, but not by the standards of the corona. And then way buried down in the inner quarter radius of the sun, where the temperature has gone back up and is about 15 million degrees in the inner quarter radius or so, that's what we call the core of the sun. And in the core, the temperature is really high, 15 million degrees, and the density is really high. And that's where thermonuclear fusion takes place, where hydrogen nuclei are fused together to form helium. Now, as I said, the sun is dear to us, and we love it very much, and we wish we could see it more than we can here in Ithaca. But in fact, it's a pretty middling star. It's boring by star standards. And what I mean by that is most stars are either larger or smaller than the sun. So here you have the sun in comparison with some stars which are visible to the naked eye in our sky, as seen here on Earth, and they're much bigger than the sun is. Most stars also don't have the same surface temperature of their sun. They're either hotter or they're colder. Most stars also are either more luminous or less luminous than the sun. And most stars are either more massive or less massive than the sun. And also, most stars are either older than the sun or younger than the sun. In fact, there are many more that are older than the sun that are younger. And so we just have to keep that in mind that we're observing our sun and it's very familiar to us and we understand it. It's in its sort of middle age in terms of its lifetime. But there are a lot of other stars that are either very, very young or are getting close to their death. And so we need to think about that as we talk about what happens when a star dies. So to start off and put ourselves in this perspective of what is the future of the sun, we're going to take a look at the brightest star in the sky. So here's a view if you could go out tonight and look at the sky. In the early evening, in fact, you would see the constellation of Orion. Here's Orion the Hunter. Here's his belt. And then if you look down towards the horizon from his belt, you would see the brightest star in the sky, which is the star called Sirius, the dog star. Now, if we take an image of Sirius with a telescope, Sirius is so bright that it kind of saturates the photograph. And that's why you get this thing that looks like this cross with these spikes coming out. That's due to the fact that light scatters inside a telescope and produces these artifacts. These are not real. This is not part of the star. This is an artifact of observing the star with a telescope. And so here it is, the brightest star in the sky. And if you look at this image, besides the weird effects of the telescope, we have learned since that Sirius is actually not a single star, but a binary star. In other words, there are actually two stars, one of which is very luminous, and that's the one that you see easily. But the other one is this little faint object. It is also a star. What do we see in this picture? It is much fainter, which means that since they're both at the same distance, it must be much less luminous than Sirius, which also means that it must be much smaller than Sirius. But they're in orbit together, and so they started out being the same age. But Sirius has become what we call a white dwarf. It has already gone through its death throes, and that is a white dwarf. That is what the sun will become in something like 5 or 6 billion years. So don't worry about it. It's not going to happen soon, but that's what the sun is going to become. So again, back to my just little quick little diagram. We think we understand the structure of the sun. What we're interested in really, what makes the sun shine today, is what's happening in the core. The hydrogen is burning into helium in the core because the temperature and density in the core are just right so that thermonuclear fusion of burning hydrogen into helium goes on for billions of years. And that's kind of important to keep in mind for two reasons. Number one, the sun is going to burn like this for a long period of time in a very stable, well understood manner, which is why life has been able to evolve here on Earth because the sun has been shining roughly constantly over the last 4.5 billion years. But it also leads us to ask the question, what happens when all the hydrogen in the core of the sun is converted into helium and it runs out of the fuel for the thermonuclear reactions? And the answer is bad things happen. So let's also remember what keeps the star from either blowing up or collapsing is the fact that the thermonuclear reactions in the sun, which are generating energy, converting hydrogen into helium and generating energy, that energy is being released from the sun in the form of radiation. At the same time, anything that has gravity is being attracted towards the center of the sun. And so there's a balance for the sun to exist for a long period of time. There has to be a balance between the outward pressure of the gas and the thermonuclear reactions taking place in the center of the sun and the inward pull of gravity, which is trying to cause the material to collapse. And that is what we call equilibrium. And in any star, if there is equilibrium, then the star can exist and burn its fuel and balance the inward pull of gravity. But if the balance is upset, then either the star will explode or the star will collapse. So remember that stars that we see in the sky that aren't doing something crazy like exploding are in their state because there's some kind of a balance of the inward gravitational force and the outward pressure force of the thermonuclear energy generation in the core. Okay, so the sun shines because of the thermonuclear fusion that's going on in the core, and the whole structure of the sun. As you can see in my diagram here, where there are different zones, and we can tell you roughly how the pressure increases as you go to the center and how the temperature decreases as you go from the center to the outside, with the exception of the corona, which is fueled differently, if you will. The sun is structured so that the thermonuclear reactions take place at just the right rate to balance the gravitational inward pull of the mass of the sun. Other stars, the bigger ones, the smaller ones, the more massive ones, the less massive ones, they have different structures than the sun, although they're similar to this. And again, if we know the mass of the other star, we can kind of figure out what its cartoon cutaway diagram would look like. Okay, so again, back to our little lesson on what has to take place. We have to have what we call hydrostatic equilibrium. The outer pressure of the gas balances the inward gravitational force of the matter. If there's too much fusion that takes place in the center, then the core will expand. When the core expands, the density goes down and it cools, so the fusion rate goes down. And then when the fusion rate goes down, it will contract a little bit, heat up and become more dense, and then we can repeat the cycle. But as long as this is balanced, the structure of the star is balanced, the star can continue on in its merry little way, undergoing thermonuclear fusion of hydrogen into helium for billions of years. The sun has been in this state for about 4.5 billion years and will stay in this state for another 4.5 billion years. But as I alluded to before, at some point in 4.5 billion years or so, the sun is going to burn all of its hydrogen into helium. And so its thermonuclear reaction rate is going to go down, and then it's going to go through a period of something like 1 billion years where it burns a little and then stops burning a little and then burns a little more and stops burning a little more. It doesn't do it quite stably. In places in the very, very core, it might actually be able to convert helium into carbon and oxygen using thermonuclear processes, but it can't do that for billions and billions of years. It can only do it for something like hundreds of millions to a billion years. So at some point, about a billion years after it finishes its current phase of hydrogen burning, it will run out of helium in the core. The core will consist of carbon and oxygen, and the core can't burn those because the sun is not massive enough to ever get hot enough and dense enough to burn carbon or oxygen. And so the core will collapse. That collapse will produce a lot of heat, and the sun will blow off its outer layers in what we call a planetary nebula. Now, and here are a couple of examples of planetary nebula. There's a core of the star at the center left behind, but the outer parts are blown off. Now, let me also give you the caveat that astronomers are terrible at naming things. They either give them weird numerical addresses or they give them names like planetary nebulae, even though they have absolutely nothing to do with planets. So don't be confused. They're called planetary nebula, but they don't have anything to do with planets. What you are left with is the outer layers get blown off, and you're left with a central object which is composed of carbon and oxygen nuclei. And that is what we call a white dwarf. And that is what the sun will become. So here we have a red giant star, the sun. If we look at the scale of the sun, here's the scale of the size of a white dwarf. It's roughly the size of the Earth, but it has a surface temperature of 10,000 degrees, even warmer than the sun. And a teaspoon of white dwarf material would weigh 15 tons, which after fiddling around, I figured out is the weight of 3 pennies. And we're all old enough to know what a penny is. The collapse of the core is halted not by thermonuclear fusion or anything like that, but by the fact that electrons don't like to be too close together. They like to repel each other. And it's the repulsive force of the electrons which stop the collapse of the core. And that idea was worked out in the 1930s by Subrahmanyan Chandrasekhar, who figured out that, okay, we have this carbon-oxygen core, there can't be any more fusion, the core collapses, but because of the electrons, if the mass of the core of the star has a mass less than 1.4 solar masses, the star will configure itself into a stable object that is the white dwarf. And so this is what's going to happen to the sun, because the sun has a mass 1 times the mass of the sun, or what we call 1 solar masses. It will lose some of that mass when its outer layers explode, but it will be less than 1.4 times the mass of the sun, what we call the Chandrasekhar limit, and so it will become a white dwarf. So what happens after that? Well, if we can hang around long enough, well, we can't, but if someone can hang around long enough to watch this, what do we have? We have a carbon-oxygen core the size of the Earth, but the mass of maybe 70% the mass of the sun. It's not producing any energy, but it has a lot of heat energy stored in that core, which it radiates into space. Over a long period of time, billions and billions and billions of years, that radiation will cause the white dwarf to cool down, so it will become dimmer and redder like an ember, and eventually it will be too faint to be seen, and then it will be called a black dwarf. But again, that's not going to happen to the sun for billions and billions and billions of years. So that's the death of the sun. Again, not terribly exciting, but we do know that these objects exist and we understand them pretty well. So what we can say is the final outcome of a star like the sun, which if it has a mass of less than 1.4 solar masses, is an object that is the mass of the Earth, still a very large density, and we understand what keeps it from collapsing further. We also have to keep in mind that what's important is not the mass when the star initiated. That is important, but what we really need to know is what's left in the core after it goes through its planetary nebula phase. Okay, so now let's ask the question, what happens to more massive stars? Because I've alluded to the fact that more massive stars are more interesting in general. Um, more massive stars are more interesting because they are able to burn higher, heavier elements in their cores because their cores are hotter and denser than stars like the sun. So they can burn heavier elements. They also burn more furiously or ferociously. So they actually have shorter lifetimes. So while the sun has a lifetime, if we go from the beginning to when it becomes the white dwarf, of about 9 or 10 billion years, massive stars might live for only 100 million years because they're really gas guzzlers. And this is interesting because it means that more generations of high mass stars have lived and died than stars like the sun, which again is kind of middling. And the final stages of evolution of massive stars are really important because they produce more complicated nuclear reactions and therefore involving heavier and heavier elements. And they also undergo much more catastrophic explosions and produce more exotic remnants. So, again, the idea is that all stars in their long-time stable phases convert hydrogen into helium. But if you go to these massive stars, and in this case, we're really only looking at the central regions of the star. So we have a really massive supergiant star. In the central regions, they're not just burning hydrogen into helium and maybe helium into carbon and oxygen, but they can also produce silicon. They can fuse silicon, or they can fuse oxygen, or they can fuse neon to make heavier and heavier elements up to the element, the nucleus of iron. And so that is how we can make heavy elements from hydrogen and helium, carbon, neon, oxygen, magnesium, silicon, aluminum, up through iron. But iron requires, if it wants to fuse, so you take if we're to take two iron nuclei and fuse them together, you'd need an enormous amount of energy, more than a stellar object can normally fuse. And we reach what's called the iron catastrophe. So in stellar evolution, we end up with a star whose core, remember the core of a star like the sun was just carbon and oxygen. But in this case, you can also end up with things like silicon, and you can end up with an iron core. Iron nuclei will not fuse together. The center of a star is not hot enough to do that. And therefore, the core can't hold itself up. There's all this heavy material above it. The core collapses and you get what we call a supernova. Supernova are amazing events that take place in the fraction of a second. And we think we actually understand the mechanism pretty well, although not 100% perfectly. But basically, within a tenth of a second after the star reaches the point where all of its nuclei in the core are now iron and can't burn, that core, which might have a mass of 20 times the mass of the sun, it collapses. In about half a second, a burst of neutrinos is emitted, and we have detected neutrinos from supernovae. And within 2 hours, the outer part of the star is explosively ejected. And when the photons that are generated in that core collapse reach the surface of what was the star before, the star can brighten by a factor of 100 million. Suddenly, a single star in a galaxy which contains billions of stars can become brighter than the rest of the galaxy. Over a period of months, the remnant expands. So these are what we call supernova remnants of gas, which are the outer layers of a star which exploded sometime in the past. And in the center, if we look at these, we would find a compact object, which is the remnant core. And we'll talk about those and what those are in a minute. The other thing is it carries off all of the heavy elements of silicon, helium, carbon, oxygen, nitrogen, magnesium, aluminum, all that stuff that was created in the region around the core and through the process of stellar evolution out into the interstellar medium. And the stars that formed after this star died would be able to form with those elements in them. So when Carl Sagan said, "We are stardust," it's because we're made of supernova material. So here's a supernova called supernova or supernova remnant, the remnant of a supernova which was visible to the naked eye in 1006 in the current epoch. So not so long ago on cosmic scales. And here's the other one just to show again that while we kind of have this simple picture, I had this simple picture that I showed, this my cartoon. Remember that no cosmic explosion, no object that we look at is perfectly round. Everything happens a little more in more complicated ways than our little cartoons like to imply. So this is a supernova remnant. This one is an older remnant that was some 50,000 years ago. Okay, so now we get to the point of what could be the final products of these massive stars. And there we have some options, and it's the options that I want to talk about. So let me review the options, and then we'll talk about the others. So again, when you have this supernova explosion, it's a really catastrophic event that produces a huge amount of energy. And we don't know in any one case exactly how much of the outer part of the star is going to blow away. And what we end up with as the final remnant depends on how much of that stuff is blown away. It could be a white dwarf, it could be a neutron star, or it could be a black hole. And we've talked about the white dwarf. It has to have a core mass of less than 1.4 solar masses in order to be held up by these electrons fighting together. If we have a more massive object, up to about 3 times the mass of the sun, it will collapse to be the size of Manhattan. And rather than weighing a teaspoon weighing 15 tons, it will weigh 10 million tons. And it's held up because neutrons also don't like to be packed entirely close together. Or if we have more mass than that in the core, say about 5 solar masses, we end up with collapsing it even further down to less than 5 kilometers in size. And in that case, nothing stops the collapse, and we end up with a black hole. Let me just point out that if we start out with a 25 solar mass star, it is possible for it to become a white dwarf if that supernova blows off 24 solar masses. And we don't understand why some supernova might blow off 24 solar masses of a 25 solar mass star, or another star might only blow off 5 solar masses. That is something we don't understand. Okay, so let's talk a little bit about the neutron star. Again, neutron stars are pretty exotic. They are have a mass of maybe 2 or 3 times the mass of the sun, but a size of um, Manhattan. So 10 or say 15 kilometers in diameter. And what holds them together is the fact that in the white dwarf, we had the electrons, which were separated from the nuclei. They were holding the star up. But in a neutron star, the protons and the electrons are forced together to make neutrons. And then it's the neutrons that stop the collapse of the star. And here's an example of a supernova remnant. Here's another one, the Cas A supernova remnant. In fact, in the center of this supernova remnant, there's a single star, which we believe is a neutron star. So, a neutron star, to fill in our little diagram here, again, has a mass of less than about 3 solar masses. It's the size of Ithaca or Manhattan, and it's held up by neutron degeneracy pressure. If we make a little cartoon of it, it has a very solid crust made of neutrons and other particles. And then inside that, it has a heavy, weird liquid interior, the structure of which we don't entirely understand because the state of the neutrons and other particles inside that star is just incredibly weird. The surface temperature of this object is 100 to 1,000 billion degrees, which is a big number. So again, we don't understand them exactly. However, we know they exist. And one of the most interesting ways we know they exist is because some of them, when they are relatively young, after having been formed in the supernova, are rapidly rotating 10 or Ithaca-sized objects with 3 times the mass of the sun, so they're incredibly dense, and they rotate rapidly with periods of rotation of a fraction to a few seconds. And they're highly magnetic, and so we end up seeing a signal where there's no radiation, and then we get a lot of radiation, and then it goes on, as if you were seeing a lighthouse. This is observed at radio wavelengths, and we only see the object when its lighthouse beam is pointing directly towards us. Because these are we see a pulse of radiation that repeats at regular intervals. These are called pulsars. The duration of the pulse is a fraction of a second, of order 1/1,000,000th of a second. And the period of the rotation is something like a fraction, 1 to 10, from milliseconds to seconds. And I propose that another lecture I'll give later on down the road is what forms neutron stars, what we know about them, and what they can teach us about relativity. But this is where we stop for tonight. The famous Crab Nebula, discovered in 1731 by John Bevis and included in Messier's catalog, contains a pulsar, which is observed not only at radio wavelengths, but it turns out it's also visible pulsing at optical and X-ray wavelengths. Its period is 33 milliseconds, which means it has a mass of about twice the mass of the sun, the size of Ithaca, but it's spinning 33 times per second. And we also see that the period of the pulsar's rotation is slowing by 39 billionths of a second per day. We can actually observe that. So we understand these objects. So I'm going to say that neutron stars are really interesting and we should talk about them sometime. But in fact, they're not that interesting. They're not as interesting as black holes. So let me just quickly go over what a black hole is, so that you can understand again that we have a sense that black holes exist in this form as the result of the process of death of a very massive star. So while white dwarfs had a limit on their size of about 1.4 times the mass of the sun and are held up by electron degeneracy or the electron pressure, neutron stars are the result of the evolution of through the supernova phase of a more massive star, but can end up with a mass of less than about 3 times the mass of the sun. Then the protons and electrons are forced together, or we get neutrons, and they don't want to be pushed any closer together. But if you have an object that has neutrons and it's more than about 3, 4, 5 solar masses, again, we're not 100% sure of what the limit is, then the neutrons cannot repel each other and the star continues to collapse and we get what we call a black hole. So let's talk very briefly about black holes. So again, we fill in this diagram. The final outcome of a star's evolution depends on its initial mass and also how much mass it loses in those explosive late stages of life events. So we can have the white dwarf or the neutron star, but if the mass of that core is greater than about 5 solar masses, then we end up with a situation in which, as far as we know, there is nothing that can hold the star up and prevent it from collapsing. And so, therefore, according to our understanding of what black holes are, this would be a stellar mass black hole. So what is a black hole? A black hole is simply an object that is so massive for its size. So remember, it's not just its mass, it's the mass for its size, is so great that a photon of light cannot travel fast enough to escape from the black hole. So in other words, if a photon is generated inside the black hole, the gravitational field of the black hole prevents the light from escaping. If we think about a satellite, a rocket like Artemis, and it's going to go up there, its orbit is determined by how the force associated with its motion, which is mass times acceleration, balances or doesn't balance the gravitational force exerted by the objects near it. So if it were in orbit around the Earth, it would depend only on the mass of the Earth and where it was in its orbit. When Artemis goes to the moon, it's accelerated towards the moon and past the moon, but the moon then pulls on it and gets it to move in a different direction, to stop moving away, pulls it back, and if they calculate the orbit correctly, it then comes back to the Earth. But if the force of motion exceeds the gravitational force, then the satellite could escape. In terms of a black hole, the escape velocity from the black hole is greater than the speed of light. General relativity tells us that nothing can travel faster than the speed of light. A black hole is an object of any mass that is so dense that its gravity will not allow light to escape, and that's why it's called a black hole, because light can't escape from inside it. But this understanding allows us to figure out how big a black hole of a given mass can be. And so a black hole is an object of a given mass whose radius is smaller than what we call the Schwarzschild radius, which in turn is the size of an object of a certain mass that inside of which the escape velocity is greater than the speed of light. I know you have to wrap your head around that a little bit, but I hope it will make a little bit of sense. Now so one of my points here is we understand the basic physics of this. We don't understand all the details, but Einstein's theory of relativity predicts that if you have a super dense object that for its mass is so small that its escape velocity is greater than the speed of light, then nothing can escape from it, and that is a black hole. So just to understand that in general, according to the theory of relativity, a black hole could be of any mass as long as it was really small. So if we had an object that had the mass of the sun but was only 3 kilometers in radius, it would be a black hole. We don't know that any of these objects exist, but theoretically they could. If we had an object the mass of the Earth, but it was only 9 millimeters across, teeny tiny, that could be a black hole. But again, we don't know that any of those exist. What's important about the black holes that we're talking about at the end of the stage, the life of a star, is that we know that some of these objects exist. And so that's what I want to show you in the last few slides. Stellar mass black holes, again, have masses that are larger than about 5 solar masses, but they're black. So how can we see them? In the context of stellar evolution, we know that about half of all stars are in binary stars. It turns out the sun isn't, but that may be why we're here, because again, the sun is a middling star in a benign part of the universe, and that has allowed life to develop. In other places where there were more dynamic, exciting things going on, it might be harder to have life develop. The way we can see a black hole is because if you have, for example, a binary star system, you might expect around the star that is the black hole, there may be some other material swept off its companion star that is spiraling because it's moving fast. So it doesn't just fall straight into the black hole. It forms what we call an accretion disk around the black hole, but it's being accelerated and heated up, and so it gives off radiation. And so again, in the context of stellar evolution and the fact that half of all stars are in binary systems, we understand that we might be able to see stellar mass black holes if they are in binary stars. And so here's our picture. We have a black hole and we have another star. And the two of them are orbiting around a common center of mass, and possibly an accretion disk forms, and sometimes perpendicular to the disk of this accretion disk, we expect to see a jet form. And so the way we can understand that there is a black hole is we can observe this star, the blue one on the side. We can observe that one. We can watch it move around an unseen object. We can see X-ray emission, which tells us that there's hot gas in the system. And by combining the information that we get from making different observations, we can figure out that if this star has a certain mass and is in a certain orbit, then this object, which we can't see directly, has a mass of more than 5 solar masses and is very compact and we can't see it. Therefore, it must be a black hole. So in fact, one of the first objects this is an artist's rendition again. We don't see it this nicely, but there is an object which is the first X-ray source discovered in 1964 in the constellation of Cygnus. So it's given the clever name of Cygnus X1. It actually consists of 2 massive stars. one of which, the one that we can see, has a mass of about 29 solar masses. It's visible, it's blue, it's a supergiant star. It's observed to orbit around an unseen companion with an orbital period of 5.6 days. We can watch the X-ray emission, and we can watch the blue star, and it varies in its brightness a little bit with a nice periodicity of about 5.6 days. So again, we understand what's going on. And when we combine all the information, we conclude that this object at the center, which cannot be seen, the X-rays are seen, but the object at the center, which we believe is the black hole, has a mass of about 20 solar masses. So this was discovered in 1964. In 1978, the famous theorist Stephen Hawking bet the other famous theorist, Kip Thorne, that this object was not a black hole. Kip was relying on the observations. Stephen Hawking didn't want to believe it. Although actually he was hoping that he would lose the bet because then they would have proved that a black hole existed. And Stephen Hawking conceded the bet in 1990, and I just thought it was interesting. The payoff was a year's subscription to Penthouse. So I'm going to stop here by previewing a future lecture, which I will give sometime on more information about evidence for black holes. They're interesting because Einstein's theory predicted them. So again, finding black holes proves that Einstein was right. They also produce some weird effects. So they allow us to test Einstein's theory of relativity, and that's one of the things that I'll try to talk about sometime. And they're just plain weird because relativity is weird. I said before that black holes theoretically could be of any mass as long as the object was so small that its escape velocity was greater than the speed of light. We now know that at least three classes of black holes, astrophysical black holes, actually exist. The one we talked about today were the stellar mass black holes. We understand how they form. We understand how we can find them. And we have found there are maybe 30 or 40 really good cases for stellar black holes. They have masses of somewhere between 5 and 20 solar masses. We also have very good evidence that black holes exist that have masses of 10,000 to 20,000 times the mass of the sun. They're not single stars produced by the evolution of high mass stars like the stellar black holes. And we don't understand exactly how they're formed. We think they're formed at the centers of galaxies and of another object, a collection of 100,000 or so stars called globular clusters, and maybe elsewhere. We understand them less, but we believe that we have found some. And then the third kind are the supermassive black holes of 1 million to a few billion solar masses, which are found in the centers of galaxies. And I gave a talk about the one in the center of the Milky Way galaxy a year or two ago. But anyway, sometime I'll talk more about black holes. But let me finish up tonight by just saying that David Brown isn't here tonight. He and Nina are flying back today, but he's convinced me that I should talk about dark matter and dark energy. And so I'll do that next month. But let me stop there.